Hi. So today, now we are going to discuss about how the deep learning concepts or the deep learning technologies are applied with natural language processing. Because in natural language processing, the conventional techniques that are used that we learn throughout the subject are mainly uh, relevant to kind of symbolic AI. That means when it comes to learning some knowledge from the text or symbols that are there in the text, like words and sentences, what we are really doing is we are trying to uh, consider each of these words or sentences, mainly the words, as symbols, and then we are going to get some statistics out of them. But however, its accuracy compared to the human level of accuracy when it comes to tasks like uh, t- trans natural language translation, summarization, and so on. Uh, these conventional natural language processing systems are lagging so behind. So it cannot be compared with human level of text processing, natural language processing. So, but with the development of deep learning, uh, people, mainly the data scientists, could able to map these requirements that we face with natural language processing uh, and apply them into their domain of deep learning, and were able to develop models that can perform really well, even better than humans do. Right? So we are going to discuss what are the techniques that are used in deep learning relevant to natural language processing, why they are important, why they are working really well compared to the traditional natural language processing techniques, and how they are implemented, not too much into detail, but in the architectural level, how the deep learning networks are designed for natural language processing tasks. And we will discuss how the latest uh, natural language processing related technologies that are breaking through the technology field and throughout the world, like ChatGPT. So we will discuss how they are designed, and you will get some basic understanding what are the principles behind these developments. So, so, so let's discuss about the traditional uh, natural language processing techniques, uh, which can encode the symbols, mainly the words or the documents, into some numerical format. Right? So mainly the bag of words and TF-IDF are the commonly used techniques that are used to uh, take these take the content, the semantic from the uh, text into a machine learning domain. But when it comes to these approaches, we actually break the sentences or the text into the tokens using a tokenizer, and then the sequence of words or the sequence of sentences uh, that were there in the original sentence or the document get lost. So what we end up with are a set of words or a set of sentences where we are calculating just the sequence, just the frequencies, the statistics of these words. Right? But when we are making these statistics, we are actually losing a lot of information that are relevant to the sequence of these words. So for this example, let's take these two sentences like Samuel hit John. So there are three words, and you can see the words are Samuel, hit, and John. Right? And another sentence, we can say John hit Samuel. So if you consider the statistics of these three sentences, you can see if you calculate the frequencies of each of these words, like Samuel, the hit, and John, all of them are similar, whatever the way that you find the frequencies of these two sentences, right? But the meaning are completely different. In the first sentence, the Samuel has uh, done it, like Samuel has hit the John, but in the second sentence, not Samuel, but a John has hit Samuel, right? So the meaning is entirely different, but if you just use some bag of words or TF-IDF like techniques to get the semantics out of these kind of documents, if they're supposed to come, if these are some documents, text documents, or the frequencies or the semantics would be measured as the same, but the real semantic is entirely different, right? Because of that, so this is just an example. So there are a lot of examples like that. So that means when it comes to a sentence or a sequence of sentences, there can be a lot of differences in meanings than its constituent set of words, right? So which are mainly generated from their sequence, how in the position where each of these words are located, right? So it is very important if we could find any learning technique where we can preserve the sequence of information. So like which word came first, which word came second, and so on. And if the machine learning model could learn these information instead of statistical techniques like bag of words and TF-IDF, uh, so then it would have been better, right? So then it would be able to predict or do the NLP tasks better than these traditional techniques, right? So that is where the deep learning or the neural networks community, these technologies has helped the natural language processing techniques to give a huge breakthrough in their development, right? So so here we are discussing about recurrent neural networks. So before that, so let's see, if you not know about neural networks, it's a neural networks or the so, correctly speaking, the artificial neural networks are the are some nature inspired machine learning technique where uh, humans have started to observe how the neurons in animals are working, their mechanism, their their learning mechanism, and how it is working inside. And people have tried to mimic these techniques in a simple way, mainly a very coarse way, not in the exact same way they could be able to clone, but they are trying to mimic it in a very simple way, and they have developed some artificial copies of the natural neurons and neural networks. Neural networks are how the neurons are organized together. So people were able to develop some artificial simulations of the kind of simulations of neural networks in their computers. So, and they were very successful at take at machine learning by applying these kind of neural networks at machine learning, and it has taken some huge steps in recent past. And in some of the tech, these huge big breakthroughs are relevant to natural language processing as well. So before we going to discuss about that, so we have to learn how the deep learning or this neural network technology has connected with natural language processing, right? So before that, so we have just discussed what are the neural networks, right? And when the neurons are organized in neural networks, uh, these neurons are organized in layers, and in the layers they are organized in different depths. So when the depth of the number of new layers in a depth in the sense of depth is high, they are known as deep neural networks. So we don't have to think too much about how deep neural networks are organized and how they are learning. But what we need to know is how the neural networks are helping to the natural language processing in this case. So when it comes to these deep neural networks, uh, we are going to first look at a specific form of deep neural networks known as recurrent neural networks. So these recurrent neural networks are a special architecture, special form of neural network architecture where you can the idea of this recurrent neural network is that they can model a sequence of events, right? So an event is something that you can model in the nature, like the things that happen in day to day, like how, like when the uh, temperature is changing throughout the day, and how a ball is changing its position in the football uh, ground, and so on. Everything can be changed. Everything that is changing with time can also be modeled as a sequence of events if you sample them with a certain fixed time interval, and also the things that happen discretely, uh, like how many uh, events, like deaths are happening in road accidents from in day by day, and all those things events are can be considered as a sequence of events where you can measure them in a numerical format, and then you can analyze them as a sequence and analyze these sequences using this deep sequence model, which is based on the deep neural networks, and you can get some higher level of accuracy when it comes to modeling these events in some of the cases, right? So that is the type of these RNNs are the type of neural networks that we are going to discuss mainly in our natural language processing. So let's see why we are going to discuss about focusing about recurrent neural networks in this lesson. So here, remember that recurrent neural networks are designed to model a sequence of events, right? So events can be in certain format where if when we are modeling to a sequence of events, an event should be in a numerical format, basically a numerical vector, right? Or therefore the sequence of events should be a sequence of vectors, right? If it is a time series related data, so then uh, it should have been sampled in the time-wise manner where, for example, we can measure a certain measurement like the temperature of the day, hour by hour, and we can record them as events. So that this is just a simple numerical value, but when it comes to complex stuff like the position of a ball or the formation of clouds in the air, in the sky, when it comes to predicting, forecasting the weather, so those are complex events. So there are different ways that you can model these complex events into a vector so that it can be represented in a numerical format. So a sequence of events means we are going to model a sequence of vectors using these kind of neural network models like recurrent neural networks. Right? So this is how a recurrent neural network looks like, but just don't get confused by its complexity, because actually we are not going too deep about how the deep learning techniques are designed inside the design to uh, create in this kind of neural networks. But what you have to know is that in recurrent neural networks we have uh, certain data processing blocks, right? So don't think what is happening inside at the moment. Like in this case, just consider them as a set of data processing blocks where I would do some vector processing, like vector addition, multiplication, and so on. So in this case, we call each of these steps, these green color boxes, as recurrent neural network time steps. Right. So in a recurrent neural network, we can have several time steps. Time steps means for each of the event that we get from the environment, we can have a single RNN time step. And for that means, for example, if it is xt minus 1, we have a certain time step. And for the next time step, for example, if this is the uh, rainfall we have measured in the previous day at a certain time, this is the today's rainfall we have measured in the same time, and this is what will be the rainfall that we would measure in the next day, right? So we can give these inputs into these data processing units known as recurrent neural network time steps. So each of these units can do something inside. So this is actually what it is does, what happens inside. So these are some vector uh, related processing, right? So so the real implementation can be somewhat maybe a little bit different than this one, but you don't have to know about all those things. What you have to know about this is that these inputs are given in each of the time step, and these recurrent neural networks are processing each of them. And what they do is that they are giving some hidden state known as H, which is passed to the next time step. So after the processing, it is passing some hidden state to the next time step, and it is giving some output as well. In this time step also, they are consuming not only the uh, input that we have received, but the hidden state that has passed from the previous time step, and do some processing and giving some output. Giving some output here, and some hidden state is passed to the next time step as well. Right? So if we are doing these calculations day by day, at the end of the day, the hidden state get updated and it is passed to the next state. And then output is given if we want it, right? So in day by day, these kind of recurrent time steps units are doing some calculations and do the processing and move to the next step. So this is what really happens in a recurrent neural network. So, but the problem is that this hidden state, as we discussed, contains the information of the history. So what that means, what has happened throughout the history in an encoded format, so which is actually, or which is already, which is also represented as a vector, right? So like the inputs are represented as vectors, these hidden states are also represented as vectors, and these outputs are also represented in vectors as well, right? So when we give some input into this recurrent neural networks, we have to give vectors as inputs, and the outputs will also be in the vectorized format, vectorized uh, values, right? So the problem is that when you are using a recurrent neural network uh, with many number of these kind of units, some of the information that we have learned in the earlier part of the sequence will get wiped out or get forgotten when the new information get added into these hidden state vectors, right? So in each time step, these hidden time steps get this hidden values get updated. So then the old values will get uh, forgotten step by step, right? So that is one of the main problems with this RNA. So we will discuss how they are handled and what we are going to do about it. And now we have to see why they are why these sequenced models are important in the natural language processing tasks. So we know a sentence or a document is basically a sequence of words, right? It is a if we take a text, it's a sequence of words. If it is written in natural language, it is a sequence of words. And we know that these words words that we find in a sentence can be represented in word embeddings. Right? These word embeddings are actually, what are they? So they are vectors, right? So word embeddings of each of the word represent some semantic meaning, like, for example, you may remember that if we take it, if it is queen, there's a semantic relationship between the king uh, in the vectorized format, right? So, like, which is similar to the woman and the man, right? So, like gender-wise similarity vector can be added, can be the difference between the man and the woman and the king and the queen, right? So these kind of semantic meanings are there in word embedding. So we can easily encode the words that are there in a vocabulary in word embeddings. And because a sentence or a document is a sequence of words, then we can model these sentences or documents in RNN models, right? So the RNNs can model a sequence of events, and events should be represented with a vector. So words can be represented as vectors because of the word embeddings, and a sentence or document is a sequence of words. So we can uh, model the sentences or documents using a RNN model, right? So which is the same. So it is like that means a sequence of words are similar to a sequence of events, right? So from that analogy, we were able to model this text for the natural language to a set sequence of events, and we could be highly successful. Not actually with the RNNs themselves, but the later developments of RNNs. So before that, so we will see how an RNN works, right? So an RNN, as we discussed earlier, has a uh, has several time steps. So it has a output vector as a time in each of the time step, and there's a hidden state emitting from that time step as well. Right? So when it comes to the RNAs, uh, just said that we are not really using RNNs in today's world. That means when it comes to the revolution of AI, we are not really using about RNNs, mainly because big two there are two big problems that we can uh, find in RNN models. The first one is that when the RNN models are getting longer, like when there are many number of time steps, it is very difficult to train that kind of RNN model. So we are not going to deep why they are not possible, but just remember that long RNN models are difficult to train. And the second point is that when the RNN models are getting longer, as we discussed just now, just before, as the RNNs and in each of the RNN time step, because the history is getting updated in the hidden state, a long sequence of RNN time steps can't keep track of the earlier history. So that means a long time history would not be preserved in the hidden state as we wish. So if we want to model a long sentence or a long document, so that would not be possible with RNNs, right? Because of that, so people have invented some different versions of RNNs. Actually, they are not RNNs themselves, but the time step units that are similar to recurrent neural networks, which are known as gated recurrent units, known as GRUs, and long short-term memory units, known as LSTMs. So when it comes to when you learn about RNAs, make sure that you know that both all these RNAs, GRUs, and LSTMs work the same. So when you learn a certain architecture with RNN in this lesson, especially, so you you have to think that they can also be used for GRUs and LSTMs as well, right? So because of the simplicity, we are just going to discuss about the RNN related architecture as it is the simplest form. So you can use GRUs and LSTMs as well. In the real world, actually, RNNs are not used for this kind of natural language processing models, but generally GRUs and LSTMs are used instead. So make sure that when you are trying to implement this kind of uh, neural networks, deep neural networks for your requirements, you are using either GRUs or LSTMs for natural language processing instead of RNNs, right? So because RNNs are not really practical at using for them for a significant task, right? So, but for the learning purposes, we are just discussing about RNNs here onwards, right? So when you say about RNNs, just think about how they can be applied with GRUs and LSTM because application is the same. The architecture is the same. Only the only the architecture that is inside the RNN is different from the GRUs and LSTMs, right? So if you just want to know what are the differences between the internal structure of internal architecture of RNNs and LSTMs, here I have just given a diagram, right? Just for your information, because you may, if you don't know about deep learning, you may be wondering what is the difference. So this is the internal architecture of RNN. So we are not going to discuss each of them, right? So we add these two vectors or concatenate vectors and apply the tan h and to the output here and take the hidden state like here. So the GRU is actually almost the same when it comes to the hidden state input and output, but the internal structure is different. Okay? So LSTM has actually another state known as cell state instead of the other than the hidden state. So it is little bit different. So, but there's no major architectural difference when it comes to uh, RNs and LSTMs because we can consider both the cell state and the hidden state concatenation as a hidden state, and we can implement our architecture using LSTMs, right? So when you discuss about RNN related architecture, you can use GRUs and LSTMs instead. So we are going to discuss what is happening inside and how they have helped to keep the memory long term without getting updated in each time step. Right. So because of this complex architecture, it was able to preserve the memory unless it is getting actually changed for a for a reasonable uh, logic. Other than there's a reasonable logic, these cell states will not get updated in these new versions of RNNs. Right. So but in the RNN is not that advanced, so its output, its hidden state get updated in each time step. And the history will get wiped out with several time steps. So, but in LSTMs and GRUs, these problems are handled, but not for a very long sequence, but for a considerable amount of time steps. These LSTMs and GRUs can work really well. So they can be used actually for our natural language processing tasks. So before we move into the applications, we have to know what are the uh, RNN related applications that we can do with natural language processing. So when we say so RNN, make sure that you understand we are referring to GRUs and LSTMs in practical world, not the RNNs themselves, right? So when it comes to these these RNN models, actually we can do almost everything that we want to do in natural language processing. For example, text classification, where we can where we do the spam detections in uh, email inboxes, and topic classifications of documents, whether this article belongs to this topic and this article belongs to this topic and so on. This document belongs to this topic. This is about the war. This is about economics. This document about tourism. This document is about entertainment and those kind of topic classification. And sentiment analysis, which is about this news is bad, this news is happy, this news is sad, and those kind of sentiments. How we can classify a text uh, into the sentiment involved in this text. So those are belonging to the text classification. Those text classification is possible with uh, these RNN models. And the other thing is text summarization. This is a complex thing, right? So with traditional natural language processing, this is almost impossible, right? So text summarization, that means you have, when you want to read the large news article, for example, and if you want to create a 5 sentence summary out of the news article, that is known as a text summarization. So this was not that much possible with the earlier techniques before the deep learning came into the arena. But with these new techniques, new technologies, with deep learning and RNN related technologies, you can now do the text summarization with considerable accuracy as well. Right? And so here actually we are not meaning about the, not just referring to the uh, RNN and RNN's derived versions like GRUs and LSTMs, but even modern versions like transformers that we are going to discuss today. So here we are discussing about how this deep learning and the deep learning models are actually facilitating when it comes to uh, text analytics, right? So the other thing is natural language translation. So uh, as like the text summarization, there was no good natural language translation technique that was available with traditional natural language processing. So with the deep neural networks, these RNN models and the later uh, transformer models, this natural language translation has become possible uh, with a higher accuracy level compared to a human. like not means higher, like that means which is very closer or even higher to than humans when it comes to natural language translation. So you know that, right? So the natural language translation means if you want to translate an English uh, book to a French language, book to the French language, that is known as natural language translation. So generally only people were able to do the natural language translation, but now these AI models can, these machine learning models can do the translation it's, itself with very uh, very easily, right? So not that much. There may be some issues or uh, unlikable stuff you may find with machine translation, but uh, it is very accurate and significantly better, significantly accurate compared to the human, you compared to human translator. So this is one of the most another important task that was possible with deep learning, right? And the other most significant thing is question answer, like chatbots and search engines. So uh, you might have already known about this ChatGPT thing, right? So in ChatGPT is actually a question answering chatbot where it can maintain some context, even some context about the questions that we ask, but and also it can create a very comprehensive, very intelligent answer, sometimes even better than humans when it comes to answering questions. So this is actually uh, I personally believe is like something relevant to artificial general intelligence, right? It's more than uh, text analytics stuff, but actually this was learned. This question answering system was trained using natural language processing fundamental. So this is a natural language processing fundamental problem, but once it is implemented in a huge scale, it has become become an artificial intelligence system which can answer the questions even better than humans, right? That is one of the most significant breakthrough in natural language processing when it comes to deep learning, right? And also you may be able to do some traditional stuff or some stuff like named entity recognition, like identify and classify stuff like people, organization, locations, addresses, dates, and so on in a text. So which are possible, which were possible with traditional NLP as well, but these deep learning models can actually do it far better than traditional traditional NLP techniques. Right? So let's just get some understanding how each of these tasks that we said are possible are done in recurrent neural network architecture, right? So in this, the first case is text classification. Right? So what we want to do is we have some text which has to be converted into a classification. So, for example, it may be a sentiment analysis problem where it can be a happy uh, sentence or it can be an unhappy sentence, right? So it can be classified into two. So which is a binary classifier. So if it is a binary classifier in deep learning networks, we can use a sigmoid activation. So which is a function that can be used instead of the softmax layer. So if there are multiple classes other than two classes, like happy or sad, so if there are multiple outputs, like for example, if this can be mapped into a few emotions like happy, angry, shame, amusement. So if there are four uh, emotions, we can have four classes for each of these emotions. So this classification problem can be done with the deep learning technique known as a softmax calculation, right? So this is a deep learning related component, so you don't have to learn about it. So this is known as a softmax layer, so that it can do the classification. So the softmax layer and the recurrent neural part is connected, is matched with the size of these dimensions of these vectors using a fully connected layer, so which is known as a, is also known as a dense layer or feed forward neural network. So these are the new deep learning related components that we have introduced here. But the most important part here is this uh, encoder part, right? So this encoder part consists of an RNN module, right? So as I said, so in this RNN module there are n time steps. That means it can have n number of time steps. For each of the inputs, we want to give some vectors as their input. So how we create the vectors is by converting each of the input token into its embedding using a word embedding, uh, using the word embeddings, right? So here what you can see is a part of the text that we are going to convert. So we have used the tokenizer to tokenize each of the word, and we have mapped each of the word into its vectorized format using the word embedding. And these word embeddings are given to each of the time steps, right? So, and you can see now the hidden state is passed from the previous time step to the next time step and so on. But there's no output you can see here in each of the time step, because we are not interested about the output in each of the time step, but instead we are at the end of the encoder model, we are getting the hidden state, which is a vectorized encoded format of this sentence, and we can uh, do some calculation using this fully connected layer. It can have one layer or many layers, and then you can classify this content, this encoded content, whether it is happy content or unhappy content, or whatever the classification that we want to do using this softmax layer, right? So in this architecture, what you have to know is that in this architecture, we have used uh, RNN time steps or the RNN units as an encoder, where we are giving these sentences and we are encoding them, and each of the term that was there in the beginning was brought forward to the next time step in the hidden state, and the next time step the new word is also added to the hidden state, and so on. The hidden state is moved throughout the sentence or the document, and at the end you can see the vector that consists of uh, that contains the meaning of this sentence, which can be used for purposes like sentiment analysis or whatever the text classification related task, right? So here we can see there's an encoder we have used to use for text classification and get a single vector. So this is actually a many to one mapping, right? So we have many inputs for each of the words and we get a one output. So we have many to one mapping in this case. Sorry. When it comes to text summarization, what we are going to do is we have an n length input. Suppose this is the large document, and we want to summarize it into m number of words, right? So in here, what we have done was something similar to the earlier case where we have used the same document and we have taken the embeddings out of each of the word, and then we have passed each of the embeddings through the RNN sequence, which is known as the encoder. And then we have got the encoded vector here, right? So we have actually specified the word, which is an encoded vector. And we have passed it into another sequence of RNN units, which is also learned with this kind of summarization. So it can give the summary which was encoded in this vector in fewer number of words, right? So here what we are going to do is we have reduced the number of words in this sentence or of this document into a small number of words, which is the summary that we want to have, right? So this is a encoder decoder architecture we have specified. So in the encoder part, we are taking the big document and encode it into an encoded vector, and in the decoder, we have taken that vector and decoded into a small number of words, which is the decoded set of words, right? So in here, once we take the output, so these outputs are also embeddings or also vectors, right? So they may be related. So what we are going to do is, so we have to do the embedding mapping. So actually, we may not be if so. What we have to do is we may using our software specifier or something to find which is the nearest word embedding relevant to this vector, right? And we can take that vector like this. So there are several ways to take this vector, not just like beam searching and so on. We are not going to discuss here. So what we are going to do is we are going to map each of these vectors output to tokens again, which is the summary of this large document, right? And in this case, what we are doing is we are using we want to use the natural language translation with deep neural network. So in this case, we have used this sequence of recurrent neural networks, and we have given the input in English language, and we have received the encoded vector like this. So the architecture is the same, almost the same as the previous case, right? So the only difference is that in the decoder and our encoder are trained for machine translation. That means we have trained for translating from one language to another language. So in this case, we can translate from English to Sinhala in this case, right? So the only difference is in this embedding, we are using the English for the embeddings for the English language. So we are in here, we are decoding for the Sinhala language. So when we are training also, we have to use these two types of embeddings when we are training our model as well, right? So when we take the gist or the summary of the meaning of this sentence or the document, we get it in the vectorized format, and then we translate it into the Sinhala of what is there in this encoded vector, right? So it is then expressed in terms of words using this decoder RNN network. So when it comes to questioning and answering, the same technique is used. So you have a set of words which are relevant to the question, and they are embedded they are converted into the vectorized format using the word embeddings. And this encoder is able to take the meaning of this question in the encoded format as an encoded vector. And this decoder can understand this vector and give the answer as words one by one, like the earlier case, where the vectors are generated and these vectors are mapped to the words that are in the vocabulary using a technique like the softmax classifier, right? So in here, because it is English to English, so it is both are trained with the same word embeddings. And the difference is that this one is trained for asking questions and giving the answer. So you may think this is not possible, right? So this sounds kind of funny, right? So because answering a question is kind of a very complex thing, right? So but with some developments, like, so not with this kind of single layered recurrent neural networks, but some improved versions of these techniques were able to do it in real, right? So actually not even with the improved versions of these RNAs, but when you are when we have found the transform model, which is inspired by this RNN related architecture. So these transformer architectures that was developed after the 2007 the Google paper, then there was question answering was possible. So that is how this GPT was born, which is the uh, basic fundamental architecture of ChatGPT. Right. So ChatGPT is not developed using this kind of RNN related architecture, but using a similar kind of encoder decoder architecture, but with not with RNN related encoder and decoder, but with a transformer related encoder and decoder. So we will discuss what is a transformer and how it is, uh, why it is different in some simple terms, right? So this is how, if you want to do a machine translation, how we should do it. But I don't think this would be that much successful, right? So because this encoded vector would not have the understanding of giving an answer to this particular thing. But theoretically, this is possible when you have given when you are given huge number of vectors to represent each of these things, and it may be possible, but in practice, this kind of RNNs are not possible, right? So, but theoretically, this is possible, and this after this uh, RNNs and its architecture was developed in the transform architecture, this was actually possible to do the translation, right? To translate, sorry, to answer the questions. So this is one of the way that people that actually we can improve the architecture that we have explained earlier, like these text classification, summarization, natural language translation, question answering. In all of these cases, we have used a single layer recurrent neural networks, right? So in here, I am reminding you again. So in here, we are referring to RNN for all the GRUs and LSTMs as well, right? So it can be an GRU network, it can be a LSTM network, but we are here referring to them as RNN networks, right? So in this case, what we are doing is we are not just converting these words into word embeddings and giving into a single layer RNN, but there are multiple layers of RNNs that you can see. So these are known as deep recurrent neural networks, right? So in the earlier case, although there are many time steps, those are not really the deep recurrent neural network. So when you add these kind of layers, one on top of the other, then only it becomes a deep recurrent neural network. So once you develop a deep recurrent neural network or multi-layered recurrent neural networks, then you can do the predictions or do the inferences better, far better than a single layer recurrent neural network. So that is an advanced version of recurrent neural networks. But the disadvantage is that it is getting even more difficult to train this kind of neural network, because even a single layer recurrent neural network or an LSTM network is difficult because there are many steps. So we are not going to discuss the exact reason, but they are difficult. But when you increase the number of layers, it's getting even more difficult to train. It's taking too much time, and it is expensive, and it is memory consuming, and so on. But people have done it by adding 2, 3, or few number of layers on top of each other, so that we could uh, get very good results or better results than the single layer recurrent neural network. So before the transformer model was introduced, even the Google Translator was using an LSTM this deep LSTM network for say, like as I remember, like 8 layers of LSTM layers for the machine translation. That means before the transformer was introduced, they were using the multi-layer LSTM networks for their Google Translator, right? So this one is actually far better when you are increasing the number of layers. But the problem is it's difficult to train, right? So that is the only disadvantage of adding many number of layers. Otherwise, it is getting much intelligent with the number of layers. And the other type of improvement that is possible with recurrent neural networks are using bidirectional recurrent neural networks. So in this case, you can see these gray color boxes are recurrent neural networks or GRUs or LSTMs, right? So in this case, so in here we have drawn it from top to bottom, upside down, not like in these earlier cases where we have given the words from bottom and then it's given to up. In here, this input is given from the top, and it is vectorized. That means it is converted into the embeddings. If vectorization means we are given this indexes of each of these words, and then we are looked up in the table, and we have found the embeddings. These are the embedding vectors. So we have unspecified it. So they are the embeddings, and each of these embedding is given to 2 sequence in each of the directions. So if you look at this direction of these arrows, you can see this information is flowing in this direction, right? This RNN network is organized into this direction. So this RNN network is directed to this direction, right? So both this direction and this direction are of RNNs are used together, and this embedding is given as inputs to both this layers input, this direction RNN's input, and for the input as input of this layer, right? So this is given as the inputs for both of these layers. So because there are 2 different directional set of RNA, so this one is known as a bidirectional bidirectional recurrent neural network, right? And the output is also taken. So this is a text classification problem. So because of that, so we take the final hidden state output as from this direction as the output, and we can take the final outcome of this direction as the output, and we have concatenated them, and we have passed into a dense layer or the feed forward layer in deep learning. So if you don't know, just don't worry, right? And then we have moved it to a classification state, maybe a softmax classifier or something. If you don't know about that one also, don't worry, right? So the idea is that instead of using a unidirectional RNN, we can have uh, RNN sequences into the both of the directions, where we can combine those two, and we can have we can get the meaning of a sentence or a document in both of the sides, right? So that means when you want to get an understanding of a certain sentence, it's not enough to read from left to right, right? Sometimes you may have to go from right to left as well in order to understand the sentence better. So that is the idea of using RNN networks in both of the directions. So it can understand better when it comes to getting the meaning of a sequence. So the difference is that if you are able to get the whole sequence as the input, so this is the better way to understand the sequence. So it is like getting the gist of the sequence or summary or the meaning or semantic of an input. If you can get the whole input, you can read from left to right and right to left, and then you can get a better semantic of this sentence, of this sequence, using this kind of bidirectional RNN network. So if you the difference is that you can't the difference between a unidirectional and the bidirectional is that you can't use the bidirectional for all the situations, right? You can, if you want to get the summary or the sentiment or something out of text where the whole text is given as the input, then you can use bidirectional RNN. But suppose if you want to predict the next token or the next word in a sequence of words, then this is not a good way, right? So because we have only the inputs up to a certain point, and suppose we have to predict the next word. So then we can't use the other direction. This direction is not possible to use, right? Not possible to be used. So you have to use a unidirectional RNN architecture if you are supposed to predict the next token or the next word. But if your requirement is to get the meaning or the sense or the semantic of a document or a sentence where the whole thing is given, then you can use a bidirectional RNN and get the requirement done, get the requirement satisfied, right? So this is the bidirectional RNN and its application. Later, people have found that when it comes to, so this is a unidirectional RNN, so just think like that, right? So what they have found was we are for each of the time step, right? We are giving word inputs, right? But we are not giving any weight to each of these words, right? So we are actually assuming that all the words that we are giving into each of the time step are equally valuable. That is what is mean by giving the same weight, right? But the reality is that each of the word is actually important when it comes, if it is relevant to the other words of the same sentence. So, right? So if there are t number of words in the sentence, for example, then if we can use this kind of bidirectional RNN model and get their outputs and take a softmax attention, that means we find which one is most relevant, and then we apply it with the input that is given to each of the input in the main sequence, then you can find for that particular uh, input what is the most relevant in most relevant word in this sequence of inputs, in this sequence of words, right? For example, say something like the cat is in the uh, house. I went to see it. The cat is in the house. I went to see it. So when it comes to the word it, I went to see it. So it is actually the word it is relevant to the term cat, right? The cat is in the house. So it is not relevant to the house, right? What we mean by it is relevant to the cat, right? So this kind of attention model can actually understand when we are in that word of cat. This attention model can say, sorry, when we are in the word of it, right? This attention model can say this it is relevant to the cat of this word sequence. So the attention is highly given to the cat from this attention model, so that this cat is modeled with, sorry, this at so the it the word it is mapped with the cat word in this sentence using this attention model. So here what happens is this a certain word is given as higher attention when we are taking the input into a sequence model, to an RNN model. So this paper was, I think, released in 2006 or 2004, and it has actually improved the accuracy of these RNN models into a very high level. Right? That means it would increase the accuracy of the models so large so that it got very popular, and people have researched about why this attention was so important, right? So when it so intuitively we can think like that, right? So when we are reading a book or something, remem we are not keeping all the words in the book in our brain, right? So we are only taking only some of the words or some of the concepts into our brain by giving some attention only to these words, right? When you are thinking about something, we are not taking everything in our brain and going to process with each of the term, right? So we are giving the attention only to a certain part of the brain, certain thing that we know, and then only that's how we get the information from our brain, right? When we are thinking. So this kind of attention model is trying to mimic the, the attention concept that is used by humans and other living beings, right? So that may be the reason why this attention model was so successful at making predictions, so doing the inferences in this machine learning model. So people were researching how we can improve this attention model, and what they have found was, now they can use the attention model only without using this sequence models like RNNs, which are difficult to train and keep the context in the memory. If we can use something only that consists of attention and not the sequence part, how can we, whether we can do some better, whether we can develop a better neural network architecture. So after thinking in this way, people were able to develop the new model known as the transformer model. So in 2007 paper uh, known as the attention is all you need, the Google has released the paper, a research paper about this new architecture known as the transformer model, which is in this format, right? So this is actually a bit complex architecture to explain, and it's beyond the scope of our lesson. However, but we can understand there are mainly two parts in this transformer architecture, where one is known as this blue uh, this blue section is known as the encoder, and this one is known as the decoder, right? So for both of these encoder and decoder, you can see the inputs and the outputs. So the inputs for this decoder are given, This is the input given for the encoder, right? So after some processing, the encoder output is given to the decoder at a certain stage, right? And using this input given from the encoder and the input given to the decoder, it has done some processing and it was able to generate some output, right? So that is all you can see, right? It could generate some output. So this is the uh, very simplest way that you can understand this transformer neural network model, right? So after this paper was released, people have identified these two components of this model, which is the encoder and the decoder, which is very similar to the encoders and decoders that we have discussed in earlier, right? So, which is the in here we have discussed that the encoder is something that can take a sequence of words and then we can generate a encoded vector. And decoder is something that you can take an encoded vector and generate some output, generate some text, generate a sequence of words out of this encoded vector, right? The encoder is actually taking these words and generating an encoded vector. The decoder is taking that encoded vector and generating the words, right? Uh, when it comes to the transform model, the same thing happens where in the encoder you give these inputs and it is encoded in a certain way. Actually, there are two outputs that are given, known as the key and value. It is not important for you. And for the decoder also, there are some input is given, and that input is used with the encoded input that is given in this path. And after some processing, it can generate the output words or the terms that it is supposed to generate. So, like we have discussed earlier, where we explained that using the text for the text classification, we can use the encoder only, right? So using the text classification, using the encoder only model, you can classify some text. Using an encoder and a decoder, you can uh, summarize the text, right? Using an encoder and a decoder, you can translate from one language to another language. For using the encoder decoder pattern, you can ask the question and get an answer as well, right? So using these encoders and decoders, also you can do the same kind of things. So what they have found was the other people who are referring to this paper have developed new forms of architecture known as encoder only architecture, decoder only architecture, and encoder decoder architecture, inspired by this transformer model, right? So the encoder only, which is also known as the auto-encoding model, which consists of the encoder part, what it does is it can encode the input information into a into its meaning at the output, right? In the transformer, you don't have any sequence of units like in the RNNs, GRUs, and LSTMs, but you just do everything in parallel in the as a matrix. So we are not going to explain how it is done. If you are interested, you can look at the how the transform model works, right? So in here, what happens is that you are not really using a step-by-step architecture like in the RNN architecture, but this is a very fast architecture, so you can generate some output, and this will have the analogy which is similar to the encoder of the RNN architecture, right? Which is similar to the encoder part of the RNN, and it can learn the information in the bidirectional context. So when it comes to bidirectional context, what you can remember is the bidirectional RNN, right? So actually it is kind of similar, right? So that means it can, so bidirectional context means it get the understanding or the semantic of the sequence in both the directions when it comes to generating this output vector or vectors actually. So this one is actually a encoded form of this input, which can be later used for text classification and so on, requirements like this. So there are some open source implementations, like one is BERT and the other one is Roberta, right? So if you are interested, you can search these projects and see how they are working in real. And that was the encoder only model. So this one is the decoder only architecture. So in the decoder only architecture, they have used the decoder section of the transformer, which is actually inspired, which is actually analogous to the decoder part of the sequence to sequence model, right? In this case, it is known as an autoregressive model because these decoders are trained so that it can predict the next token. So earlier we said that the encoder can encode the bidirectional context and encode the meaning into a vector or vectors. In the decoder, what it does is it can get the meaning in unidirectional sense or understand the unidirectional context so that it can predict the next token which should come next, right? So this can be useful when it comes to generating new tokens one by one. If you can remember, in ChatGPT, you can see that the words are getting generated one by one because ChatGPT is actually a implementation of this GPT model. So when it comes to the open source models that are available in the community, GPT and Bloom are one of the most popular, two of the most popular models that are there, which are using the decoder only architecture of the transform, which can predict the next word in the sequence. Next word when you are given a sequence of words. And combining both these encoder and decoder together, we can form this entire transformer. So inspired by the entire transform model, this encoder decoder architecture is developed. Actually, it was proposed by this paper itself. So it is also known as a sequence to sequence model. That means it is similar to this kind of model, which is encoder decoder model, which has both the encoder part and the decoder part. Right. So in encoder only models, there's only this encoder part. In the decoder only model, there's only this decoder part. In the encoder decoder architecture, it has both encoder and the decoder. So in this case, what happens is you encode the input and the meaning is generated and passed to the decoder, and it helps the decoder to generate the next token when the first few tokens are given as this output. So this is given as output because this is given as output that has come earlier, and the next output token is generated from this point using by looking at the meaning of this input that is given to the encoder. So this is actually a very good uh, uh, application of machine translation or natural language translation. So you give, if you want to convert something, if you want to translate from English to Sinhala, what you can do is you give the English output from to this encoder, and the meaning of this English sentence will be encoded and will be passed to this decoder, and from word by word, this decoder can generate Sinhala words looking at the meaning of this English sentence, right? So from start, it can generate one word, one singular word, and then with using this singular word, it can predict the second singular term. With first and second singular terms, then it can predict third singular term or the word, and so on. It can predict until the full stop or the end of the sentence is achieved. That is how the machine translation happens in an encoder-decoder architecture. So we have discussed about the transformer model. There are subtypes that were developed later using the encoder only, and encoder-decoder architectures. And using the new form of transformer-based models, people were able to uh, generate another type of word embedding known as contextual embedding. Right? So the earlier generations of word embeddings that we have learned, like the word to a can glove, are known as static embeddings because they were trained on on a static data set, which is a very large data set. However, it is a static. That means once it is trained, so those vectors are fixed. You can't change them. You can interpret them differently depending on the context, right? So, for example, if you look at these two sentences, I sat on the bank of the river and I deposited money in the bank. Now, you know, the word bank is used in a different context in these two sentences. I sat on the bank of a river means I am referring to the river bank. I deposited my money in the bank. In here, the bank means the real bank, which where the monetary transactions are going on, right? So by just looking at this word, you can't say which vector or the which semantic should be used in either of the sentence. But using contextual embeddings, you can look at the sentence and you can find what is the relevant meaning of each of the word. So using the transform-based techniques like the BERT, you can actually find the contextual embeddings which can uh, increase the accuracy of the models that are using these contextual embeddings into a very great extent, because now we can actually understand the meaning, what is really meant by each of the term, without statically binding into a certain vector that we have trained on the global data set. Right? Now, depending on the requirement, we can change the meaning and uh, do the predictions or do the NLP tasks very efficiently and accurately compared to the static embedding. So these contextual embeddings are generated using transform-based techniques like BERT, right? BERT is just an example, right? So there can be other stuff as well, other models as well. So with this, the innovation of this transform model, And there was another advantage we were able to achieve. That was uh, the that was being able to address the problem of having less amount of data to train our model. For example, say if you have a certain text data and you want to uh, train a certain machine learning model using this text data, right? So when it comes to a deep learning model, which is very hungry with data, your data set in most cases will not be sufficient to train that particular deep learning model. But if you can train it, then this model would be giving you a very higher accuracy. But because you don't have enough text data to train your model, you are not able to get that advantage of using a deep learning model. With the innovation of this transform model, now you can uh, use a technique known as transfer learning, where you can pre-train. That means you can train this model before you are using it with your dataset, so that it can get the understanding of the nature of the stuff that is there in the world, right? How this word language is built, how these sentences are connected, how this grammar is working, right? So how the physics is working in this world, and all those things are uh, being identified by this pre-training. That means first what you do is you train the uh, BERT or transformer or whatever the transform based model with huge amount of text data, which is uh, which is known as the unsupervised learning, where you don't have to label the data and make the data sets to train these kind of models. So you can just give a huge corpus to train a transform model, and then you can use this transform model to uh, do the NLP tasks with the data that you have in a very higher accuracy level. So that is another advantage that we could achieve with the transform model. So that is why the BERT and GPT like models are now very popular and are giving a very higher uh, performance number. So benchmark tests are getting passed with higher levels for these transformer based models, because now we can pre-train them with uh, the huge amount of text data in the unsupervised learning manner, and then you can use our text data so that it could work it can easily understand our data and adapt to our data to train with our data, right? So if when you want to train a BERT or a GPT model with your data set, your text data, first you can get a pre-trained model. Actually, you can download that kind of model from the internet for free. Then you can uh, fine tune that model with your data set, and you can use it easily and happily uh, with a very short period of time, and you can get a very higher accuracy level compared to training your own model with your own data from scratch. So that is the main advantage that you can get with these transform based models. So maybe later we can discuss about how the large language models are working in depth. So for the today's lesson, let's finish our lesson for today. If you have any questions, you can ask. But yeah, if you have any questions, you can post or send me in person if you have. Okay, thank you for listening to this lesson.